So you may be wondering why the book is called Storm in a Teacup, but the title very clearly says we need to talk about physics. And that is because we do. I'm a physicist. People do not talk about physics enough. They do talk about physics quite a lot in popular culture, but they don't talk about the bits that I care about. So we're going to talk about the bits that I care about. I'm a physicist based now in London. I did work in the States for many years. I sort of became partly an oceanographer by the back door. I've done lots of different bits of physics, but I identify very strongly as a physicist. But I do all these other things as well. They're not mutually exclusive. And I'm not going to talk about my job very much, but just in case you're wondering, bubble physicist is a real job. It's very important that you know that. So physics, right? I did a physics degree. I did 3, I think. And this is the sort of popular image of physics, right? There's people off to the sides, especially over there, might not be able to see very well. The pictures aren't that important, don't worry. So this is the classic image of physics, for those who can see it. It was taken at something called the Solvay Conference in 1922. And this was when the big ideas of quantum physics were battling it out. They'd realized, the Victorians thought that physics was all just mechanisms. No, it would just be a bit of tidying up needed around the edges, and then it would all be okay. And then quantum physics became necessary, and this sort of thing happened. These big conferences of all these great minds, who you will notice are mostly old white men. Marie Curie is on the front row, they let her in. But grappling with the nature of determinism and what it meant not to know exactly where a particle was at any moment in time. So there's a lot of suits, a lot of ties, a lot of beards, and a lot of quite grumpy-looking people, to be honest. So that's sort of the picture of who does physics. When it comes to what physics is, it starts to look like this thing down here. Now, anyone who can read this language will recognize that these are wave equations, and they're describing particles. And to everyone else, it just, well, it's quite pretty, right? But it's complicated and it's inaccessible, and it is another language, and that's not the sort of thing you can just appreciate without having studied a little bit. And then there's things like that. So this is an artist's impression of the gravitational field surrounding 2 colliding black holes. And that's just weird. And then this thing is a load of lasers, and I'm just glad I didn't have to write the risk assessment for whoever took that photograph, because if a laser safety officer walked in and saw that, you would be sacked tomorrow. So, yesterday. So the point is that this is the picture of physics. It's obscure, and it's done by slightly weird people, and it's far away, and it's complicated, and it's not here. Well, I'm a physicist, and I study this, which is the surface of the ocean. So I study the way that breaking waves and bubbles at the ocean surface help the ocean breathe. And the surface of the ocean is a fascinating place. It sometimes looks like this. You will notice sometimes people ask me, I've got friends who, are marine biologists and things like that, and I've occasionally gone with them to study, nice tropical reefs in hot places. That is not what I do. I study the North Atlantic in storm season. So this is as colourful as it ever gets. But let's worry about the shape, not the colour. So the ocean surface sometimes looks like this, and I go to sea and look at it, and sometimes it looks like this, and I study what's underneath these white patches, and sometimes it looks like that, and sometimes it looks like that. And this is physics, right? There's no doubt that whatever describes this process is physics, but it's not included in that, sort of popular, the traditional view of physics. But it does count, and it counts for a very important reason. So I do this, I'm told it's called hosting here. We call it presenting documentaries, science documentaries. And a few years ago, a director we derived at, we were on the coast. We wanted to talk about breaking waves. The BBC didn't have any money, so instead of sending us to somewhere pretty with breaking waves, they'd sent us to the far side of Cornwall in January. And anyone who's been there will know that it's a lovely place, but it's quite cold. Anyway, so because I was shivering, the director sent me off to sit on a rock, and he said, "You go over there, Helen, and think about the thing you most want to say about physics." And now I look back and I'm like, he was just trying to keep me quiet and from complaining about the cold. But you just go off over there and you work out the thing that gets you the real thing that you're interested in when you think about physics. So I toddled off to the rock, and it occurred to me consciously for the first time that the thing that has always interested me most about physics as a subject is this idea of patterns. That it's not about learning a pile of facts. I mean, you've got to feel sorry for the biologists. Have you seen how many types of frog there are in the world, right? It's not just about learning all the different types of frog. Physics fundamentally is about patterns, and it's about patterns that pop up in this again and again and again and again. So, for example, the same little pattern in physics explains cake, the internal combustion engine, hot air balloons, katabatic winds off Antarctica, and popcorn. All of those things come from one tiny, tiny little sort of physical idea. And I promise this is the only equation I'm going to show you. But it's this, right? For those who like equations. It's not, even if you don't like equations very much, it is quite nice, right? It's a friendly equation. But it basically relates the pressure and the volume and the temperature of a fixed body of gas. And once you know just a little bit about that, and the idea that if you have a gas and it's at a fixed temperature and you reduce the volume, then the pressure of the gas increases. It's that sort of thing. So that one little bit of physics gets you to all of these places. And it works. This is almost universally applicable. You can find gases that don't obey that, but you have to try quite hard. Something quite weird has to be going on. So there's a pattern, and once you learn the pattern, you suddenly have access to all these different bits of things in the world. And that's the thing that gets me really excited about physics. It's like a toolbox. And then I realized the consequence of that realization, of that sort of way of thinking about it, which is that fundamentally, physicists are really lazy. Instead of just learning lots and lots of stuff, we basically learn a small number of patterns and how to use them, and then everybody else thinks we're clever. We don't tell them. So that's interesting. You know, it is a relatively small number of patterns, and they give you all of the physical world. And so there was only one equation. There are two graphs. So this we've got time going along the bottom here. So this is small time over here, sort of microseconds and things like that, nanoseconds. Age of the universe stuff down that end. And then down the bottom, on this axis, we've got small things down here, so this is size, and then big things up the top. So in that traditional view of what physics is and what physicists study, we've got cosmology, which is up there. It's very big, it's very far away, it's out in the universe, and it takes a very long time. And then down this end, we've got quantum mechanics, which is very small, very fast, far too small to see, quite weird. And it happens extremely quickly. So this is a sort of view of where the frontiers of physics are. But there's a problem. And the problem is that this is all the things in the real world. There's volcanoes and clouds and coffee stains and wind turbines and toast and lightning and clarinets and bubbles and Jupiter. That's Saturn. And they're all not they're not general relativity and cosmology, and they are not quantum mechanics. They sit in the middle. And things tend to sit along this sort of diagonal line. So bigger things tend to be slower, and smaller things tend to be faster. And all of these are not randomly placed. I actually, did the sums. So there's a general thing here. But there's lots and lots of stuff that can happen in the middle. And so when you add this, general relativity starts out there, quantum mechanics starts down here, a huge amount of space in the middle. Now, it's also not trivial. So there's a frontier of research out there, there's a frontier of research down here, there's another one in the middle. But it's not just in size and time, it's in complexity. Because when you take quite basic, simple patterns, so Newton's laws of motion, thermodynamics, a bit of rotational dynamics, a few of these basic things, they can act together in fascinating ways that build complex systems. So the third frontier in physics, the thing that we don't talk about when we don't talk about physics enough, is this middle frontier here. It's complexity. It's generally not very elegant. It's all quite messy, but it's real, and this is where we live. And that's why it's important, because we live in the messy bit. So I think that this should get a lot more attention, because this is what's running the world, fundamentally. It's the same physical laws, but this is what's going on. Now, just as an example of some of the things that are around us in everyday life that really are current research topics. Here are some pictures. Sorry for the people over there who can't see them. I still don't know what this thing's called, but it's the thing that you drizzle honey from if you're into that kind of thing. It's sort of wooden stick with notches that you drizzle honey from. I had a friend, when I was a PhD student at Cambridge, I had a friend in the maths department who spent his entire PhD in the maths department at Cambridge studying basically the sort of twizzling process as honey, because it's quite easy, right? It starts at the top, and that's all right, and it ends up at the bottom in a puddle, and that's all right. But what happens in between is genuinely complicated, and he assured us it was very important, although none of us ever understood what he was saying about that. But the point is that the mathematics of that is a frontier of current physics research. These are bubbles in turbulence underwater. This is what I study, and this is the sort of thing where there is no computer model that can predict this behavior to a high accuracy. We can do averages, and we can do statistics, and we can sort of do bulk properties. We can fudge it in various ways. We can get useful information out, but there's no computer model that can absolutely simulate the behavior of a load of bubbles in turbulence. This is the reason I have a job, because we can't do that. And yet, this process happens every time you pour out water into a glass and you see that little plume of bubbles. This is what's going on. And we understand the basic physical laws, but exactly how the details of why a bubble becomes this shape and not this shape in practice, that's a bit trickier. And then this one's quite nice. There's the egg timer here. The thing to look at is that little pile of sand at the bottom. So you'll all be familiar that if you take any granular material, so it could be sugar or flour or salt or something like that, sand, pebbles, whatever, and you pour it out, it will form a cone. And what happens is it starts flat and the cone kind of grows like this. And then it gets to a certain angle and it can't get any steeper, so it just gets bigger and bigger and bigger and bigger. And that angle, the sort of steepest it can be, is called the angle of repose. And it depends on what sort of shape the little grains are and what material they're made from and how wet they are and all these little things. And there's no simple way to predict the angle of repose. If you give someone a grain and let them look at it under a microscope and sort of inspect it, it's actually very difficult to predict exactly what the angle of repose is, because it depends on, how much they interlock and how they stick together. And yet that's the sort of thing you see in your kitchen, and it's relevant to real-world problems. So all of this is worth looking at. Now, the first thing is that all these little everyday things, they're not just toys. There's this perception that this is all just, that's what you give the kids to play with when they're bored on a Sunday afternoon. And I'm about to tell you that's not right. We should all get to play with them, and this is the reason why. So I'm about to show you a video here. One of these eggs is raw, and one of them is boiled. And we're going to watch the video, and then you're going to tell me which one is which. This is the relevant bit. That's interesting, isn't it? Right, which one is raw? This one, yeah. Now, isn't that funny? Because I don't know, does anyone in the room use that as a way of, who puts boiled eggs back in the fridge? But leaving that aside, right, has anyone, apparently some people do. It's okay, you could admit it. Oh, look, we've got a hand up there. We can laugh at him afterwards. So here's the thing, right? Probably none of you maybe had thought about that before, but you knew, right? You sort of recognized the pattern when you saw it. This one is raw, and the reason we know it's raw is that you set them both spinning, that's all right, and then when you stop, you just very briefly put your finger on the top to stop it. If the egg is solid, you stop the entire thing, so it just stops, and that's the end of it. If the egg is liquid on the inside, when you put your finger on it, you stop the shell, but the liquid on the inside is still going round because nothing stopped it. So the shell stops for a second, and then it gets pushed around by the liquid again. And the principle that this demonstrates, a physicist would call it conservation of angular momentum. And what it means is that once something is spinning, it keeps spinning unless you do something to stop it. It keeps spinning indefinitely unless you do something to stop it. And the spin axis will always point in the same direction. So that's all very useful if you've got eggs in the fridge. And people do go home and play with eggs after this. Blame me, it's fine. But this demonstrates a principle which is much more important. which is this. So this is a picture, this thing here is a picture of the Hubble Ultra Deep Field, because the Hubble Deep Field wasn't enough. And so the Hubble Space Telescope has been in space now for more than 25 years. To take this particular picture, so NASA's analogy for this picture is that if you took a drinking straw, think about that big, small, and you made it 2.5 meters long, which is almost the width of this screen, and you peered at the sky through this 2.5 meter long. Oh, you're American, aren't you? Do I have to do it in feet? No, that's okay. Good. You know, the most soul-destroying part of writing the book was when my American publisher sent me back the thing and said, you have to convert it all into feet. As nobody has measured the mass of the sun in pounds, ever. Anyway, he wasn't convinced. So anyway, point is, so you look through your 2.5 long straw, and the bit of the sky that you can see through the end of it is that, right? So there's a huge amount of detail, and Hubble had to basically look at the same bit of sky for 11.5 days to capture that image, which is all very nice. Now, Hubble has been floating in free space, not touching anything, for 25 years. How does something that is just floating, it's just nothing to push against, nothing, how does that point at something so precisely? How does it know where to point, right? That's a problem. And the answer is that on the inside of it, it's got something which is almost exactly the same as the spinning eggs, except sadly it's not actual eggs, right? It's got gyroscopes, which are spinning things, and because of the law of the conservation of angular momentum, when they're spinning, they stay spinning in exactly the same direction. There's nothing to stop them, and so Hubble can kind of effectively move around them. And it's like a three-dimensional compass. So the same principle that lets you tell apart a raw egg and a boiled egg by spinning them also lets the Hubble Space Telescope orient itself in space. It's the same physics. And yet one is seen as this trivial thing in the kitchen, and one is, making these images that make everybody extremely happy. And the nice thing about these patterns, once you start to spot them, is that once you've got the sort of habit of looking, is that you spot them in other places, and that's rewarding. It is rewarding. So I once showed that egg video to a sort of talk I don't normally do, but it was a kind of corporate group of people during the day. There was a lot of people in suits trying to impress their bosses. Don't know why I was there, but so I did my bit, and I was running over a bit in time, and so I got to the end, and I showed the egg video, and someone was flapping at me because I'd run over, and I said, "Oh, well, I won't tell you how it works. You can work it out. Come and ask me afterwards." And I cleared off the stage, and after I had these fully grown middle-aged men literally tugging at my sleeve, saying, "Is it this? Is it this?" And they explained, and I said, "Yes, yes." The sense of reward doesn't go away when you're not a child anymore. Anyway, so what some of the nicest things about these patterns is that the payoff can take a long time, but you carry it with you until it's time. So the reason there's a picture of blueberries here is that I lived in the States for 5 years, and the last 2 years was in Rhode Island, which is where they grow lots of blueberries. And I'm from Manchester in England. We don't really have blueberries. There's nothing wrong with us, we just don't have blueberries. We do now, because of international shipping and things, but we didn't when I grew up. So I was ridiculously excited by the concept of blueberries, and I'd always made lots of jam, like preserves, as a kid, and I thought it'd be great when I left Rhode Island to take home bright blue blueberry jam. That'd be really cool. So I went blueberry picking. And you should all know, by the way, that when you go fruit picking in England, if you ever come to England, Britain, you have to suffer for fruit picking in Britain, because you either have to bend down and really hurt yourself, hurt your back picking strawberries that are on the floor, or you get scratched to pieces by raspberry canes. You've got it so easy in this country. Blueberry picking is like cheating. This sort of waft along, you pick cloth, waft along a load of bushes, and blueberries fall into... It's ridiculous. Anyway, so I collected gallons, because you're in America, right? It has to be gallons of blueberries. I'm not prejudiced or anything. And then I went, back to make this blueberry jam. And you put the sugar and this stuff in the pan, and you start boiling it up. And I waited for this blue jam to emerge. And I'm sure plenty of you have made blueberry jam, and this is not what happens. What happens is that you let the boiling process happen. What you put in starts blue. What comes out is bright fuchsia pink, which is weird. And it's not blue. I wanted blueberries. Blueberry jam. Anyway, so I took it home, told everyone it was blackberry jam, and there the matter rested. But I was a bit, like, it's wrong. So 6 months later, when I was back in the UK, I had a friend who directed history documentaries, and he was making a documentary about wise women in the 16th and 17th centuries. And there are quite, these are the women who were there were one or two in every village. They were the midwives. They sort of dealt with people who were ill. They sort of picked up the pieces, doing all these little useful jobs. And so it's a lot of folk knowledge, but they wrote things down. They were systematic. And he said there are these things that keep coming up. And I'm curious to know if there's any actual science. I mean, they're obviously not testing for witchcraft, which is what they thought they were doing. But maybe there's something, maybe there's something going on. So there were a few things that he showed me. One of them was that there was a thing that said if you boil the first water of the morning, which is urine, apparently, and it goes through all the colours of the rainbow, then someone is bewitched. And I think I was bewitched if that. Think I was bewitched if I tried it, but I'd definitely think I'd be bewitched if it worked. So there were things like that. And one of those things was that if you take tincture of verbena, and verbena is one of those bright, colourful flowers that we certainly get a lot of them in the summer. You probably get them here, this neck of the woods as well. And you put it on someone's skin and it changes colour, then they are bewitched. And I went and had a bit of a think about this. And it turns out that verbena is, the bright purple and red petals, some of them. And the pigments that make them, those bright, vivid colours, are a category of chemical called anthocyanins. And they're really interesting. They're common in lots of things. If you get red cabbage, for example, that's got lots of anthocyanins in it. So that not all, but a lot of the bright vegetable pigments are in this class. And the really interesting thing about anthocyanins is that they act as pH indicators. If you're ever bored, get some red cabbage, boil it, throw the cabbage away. The water is the interesting bit because it will now be bright red. And you can go around the kitchen putting it on things, which is highly entertaining. See, because it changes colour. And if you put it on something alkaline, it goes blue. And if you put it on, if you put it alkaline, it goes yellow and green. If you put it on acid things, it goes red. That's right, from purple. Change it, and it sort of depends on the pan you boil it in as well. You can start with slightly different colours. So there's a huge range of colours. And so I worked out that your sweat can change pH depending on what you've been doing, right? Depending on what you've been eating or what, your genetics. And so if I put tincture of verbena, which just means petals boiled in water, on my skin, normally they didn't change colour, but if I did it just when I'd come back from a run, because I spent a while trying this, then they'd change colour. So I reckon what those wise women, were testing for was actually, they had a pH indicator, and they were just testing the pH of people's sweat, which was quite interesting. So we did this whole TV segment about that. And then I remembered the blueberries from 6 months beforehand, because as any of you who make jam know, when you make blueberry jam, what goes in the pan is blueberries and water and sugar and lemon juice. And so the reason that blueberry jam is bright fuchsia pink is that it's basically the entire thing is acting as litmus paper for the lemon juice and telling you that it's acid. So I didn't stand a chance of having blueberry jam. But it was almost worth it just for that little thing, 6 months later going, oh, that's why I was doomed to fail. That's useful. So you build up these patterns through life, through experience, as long as you know what you're looking for. And then they have the more serious sort of consequences. Now this another little video here. The thing to watch is, it doesn't matter that they're green. The thing to watch is how fast the slopping happens. What you're about to see is a hand come in and just sort of shake the glasses from side to side. So here's the beer glass. So it sloshes, right? We've all seen sloshing do this. But if you look at the rate of sloshing, you'll see that the bigger the beer glass, the sloshing happens relatively slowly. And the little vodka shot glass there, the sloshing happens really, really quickly. And you can imagine something further off to that end. If you put water in a bath and you slosh it, it goes really slowly. So there's a lesson here. And the lesson is that in a sort of cylindrical vessel like that, the bigger the radius, the larger the circle at the top, the slower liquid will slosh in it if you just disturb it and let it slosh back to equilibrium. And it turns out it does depend mostly on the radius. It depends a little bit on the depth and a little bit on the shape, mostly the radius. So that's interesting. And what that's called is something called a natural frequency, that any system that can oscillate, if you give it a bit of a shove, it'll have one particular rate at which it swings to get back to being still. And this is the reason that I spill my tea every day in my department at University College London. So the tea room is at the end of a long corridor, and I am British, therefore I drink lots of tea. So every morning, and I'm at work, I'm always in a hurry, so I'm never going at anything less than race pace. So I go to the tea room and I make a cup of tea, and then I race back down the corridor with this thing. Every morning I spill my tea. And the reason that I spill my tea is that my walking rate, when you walk, you're effectively, there's a bit of a sort of regular shaking of the mug in this case. And it just so happens that, so you're giving the mug a little bit of a push. And if you give something a little bit of a push at the same frequency as its natural sloshing frequency, in this case, it will make that sloshing really, really, really big. If you push it, it's like pushing a child on a swing. If you push it at exactly the right rate, they'll get higher and higher and higher. If you try and push and push and push and push, and that's too fast for the swing, they just don't go anywhere. And the same if you do it very slowly. But if you hit exactly the right rate, then you get an enormous amount of sloshing. So it just so happens that my step rate exactly matches the sloshing rate of my tea mug, and therefore, every morning, I get enormous, great big sloshing going on, and I spill my tea. There are a few solutions to this. I could slow down, not an option. I could get a very small cup, start drinking espresso, because then it wouldn't match, but I don't like drinking coffee. I use it for experiments, so I like the smell of it. I buy coffee for all sorts of things, but none of them is drinking it. The other thing I could do is I could start drinking hot chocolate with a layer of foam cream, or milk on top, because the foam dampens down the oscillations, so it kind of keeps it in. Which is why beer, if you've got a beer with a lot of a head on it, it doesn't get spilt nearly as much as it should, because the foam dampens down the oscillations. Pubs everywhere should be very grateful for that bit of physics. Anyway. So that makes me spill my tea. And so there's this matching, this is resonance. So every system has a natural oscillation rate, and if you push it at exactly that rate, you push the oscillation really, really high. That's what's going on. Tea, all very nice. But then it's got much more serious consequences. So in 1985, there was an earthquake in Mexico City. It caused a huge amount of damage. Well, the earthquake was off in the Pacific, but Mexico City was very badly hit. And afterwards, your Army Corps of Engineers went along to have a look at the damage and to see what lessons could be learned from what they found in terms of building and civil engineering. And they found something really interesting. They noticed that buildings below 5 stories high were basically fine. Buildings above 20 stories high, and there were lots of them, basically fine. It was the ones in the middle that fell over, which is weird. So then they had a look at the actual trace of the earthquake itself and what happened in the ground. And the geology underneath Mexico City, you probably know, is pretty unusual. It's in a big basin, so there's lots of sediment there. It's a very specific, it's got a hard base with this sediment on top. And the consequence of the geology, so an earthquake, the shape of an earthquake shaking is normally quite complicated. But the consequence of the geology in this case was that the foundations of Mexico City basically shook at just one frequency. So the geology amplified one particular shaking rate. And I'm sure you're ahead of me here. Tall buildings tend to sway. They're supposed to do it, it's fine. And each has a natural swaying rate. The taller the building, the slower the rate. So it happened in this case that the natural frequency, the natural swaying rate of the buildings between 5 and 20 stories high was almost exactly the shaking rate of that particular earthquake. So they're the ones where the shaking grew, and then they they fell over. So you've got a very important civil engineering consequence of a little piece of physics, resonance, which you can see in a cup of tea. And the thing is, once you know about things, you can also do something about them. So in this case, not in Mexico, but this building here, the Taipei 101, which was for a while the tallest building in the world until the next tallest one came along. This is quite close to some earthquake zones. If you don't like swaying buildings, this is not the building to go in, right? Everybody else is very sensibly not tall buildings. So this building, they did something extremely clever, and I've never visited it, but I would love to go. So in the middle of this building, sort of in that bit there, close a third of the way down from the top, inside, they put something fascinating. Now these are stories. There's people over there. So they put a gigantic pendulum 5 stories high hanging down the middle of the building, and then they spray painted it gold, because why wouldn't you? But it can sway, and it sways independently of the building. And the reason they put it there, and it's fantastically clever, is that so you've got pendulum hanging in the middle. When the building sways that way, the pendulum's kind of left behind. And then as the building sways back, the pendulum's caught up. And so the building and the pendulum are sort of swaying against each other, which reduces the overall swaying of the building to about a third of what it would have been otherwise. And there's videos of this thing. It takes about 30 seconds for it to get from one side to the other. But you can see there's videos of it, people watching it during an earthquake and watching it move. I mean, you'd have to be pretty interested to be staying watching it. But you know, somebody did. There's a video on YouTube, so you don't have to. But it's clever, right? So once you have these tools of the world, you understand them, then you can start to manipulate what's around you. And these are big, important civil engineering problems, not just trivial little toys and why you don't spill your tea. And this is the fun of science. It's those of us who are professional scientists and engineers, really, those subjects are about what you can create using these patterns. And that's the fun of it for me. Like, I like the finding things out and pushing at things, but the game I really enjoy most is that day where you walk into a lab and I've got to measure this thing and I don't know how to do it, and I've got a lab full of toys to play with. What am I going to do? And it doesn't always lead where you expect. So the reason this picture here is here. This is a natural diamond. They don't often come out like that. This one did. The rock around it is kimberlite, which surrounds most of it. So diamonds generally formed at the pipes of volcanoes. Kimberlite is the rock that they are very often found in. And the reason that this picture is here is because of a friend of mine who was in my lab when I was a PhD student, who is a New Zealander, called Jeff, but he was a Kiwi, so we all called him Jiff. And his job was to study diamonds being hit very hard. So the game here is that if you're blast mining is a great way to kind of break up rock. The problem you've got if you're blast mining and there's precious stones in it is that obviously you want to break up the kimberlite, but you don't want to break your diamonds. So Jiff was studying how diamonds break up under impact, basically. And the way you do that is you have a thing called a gas gun, which is in our case, tube about that wide, 5 meters long, and you put it's easier to move something that isn't a diamond. So you put your diamond down this end with high-speed photography and all kinds of clever diagnostics like this, something over there. Down that end is a massive reservoir of pressurized helium, and then you put this sort of little slug of plastic and rock, in this case here, evacuate all of this. So that when you release the helium, it pushes the thing down here, it hits the diamond. Now, our gas gun could accelerate the projectile to 2 kilometers per second. This is a lot of thump. And then the gun was pointed straight at the center of Cambridge. And so in order to stop this, causing lots of holes in lots of very old buildings, the thing here, which was called inventively the capture chamber, there was a huge metal sort of chamber on big chains, that big heavy thing. And so the idea was, and it was full of rags, cloth, cotton rags. And so the projectile would hit the diamond, you'd gather your photographs, the whole lot would disappear after the rags. You have a big sort of flame this ball of fire as it set the rags on fire. And the capture chamber would sway, there'd be an enormous thump, and nothing, there'd be no holes in anything. But you needed all this mass here to absorb the momentum. And you needed some rags there in order to just stop, sort of contain everything, and the fire helped. And so you needed something in there. Now, Jeff had a problem, and this problem was that he could take all these pictures at the instant the diamond broke up. But he wanted to get the bits of diamond back. And the problem is he never did, because they disappeared off into the rags with all the other mess and the fireball. And so he spent a while trying to work out what he could do, which physical tools could he use, how did he solve this problem so he'd get his bits of diamond back to see whether they'd broken up further down the line. And I will never forget the day he walked into our lab, having come from the local supermarket with these 2 big bags full of strawberry jello. I had to think what you called it then. The stuff, for making desserts from. And he plonked these down. What are you going to do with those, Jeff? He said, I've got a solution. So he's a proper scientist. So he spent 2 days working out what ratio of boiling water had to go with the jello to make the right thing. And then he took all the rags out, cleaned out the catch chamber, put strawberry jelly, because he thought because that was the solution. That the idea was the strawberry jelly would do the job of the rags, and then he could sieve it and get his diamond back. So he set this all up. He put the diamond down there, evacuated the thing, lots of helium over here. And the day came, and he closed everything down and pressed the button. So the projectile comes down the barrel at 2 kilometers a second. It goes straight into the diamond, smashes it to smithereens, and the whole lot disappears off into the jelly and the capture chamber. Now, what no one had told him, what he hadn't thought to look up, was that when you put it under pressure, jello liquefies. And so the whole vat of strawberry jelly instantly liquefied, spluttered out everywhere, and re-solidified. And he never got his diamond back. And he did spend the next 3 days clearing up. But I have enormous respect for Jeff. I love him to bits for having done it, because if it had succeeded, that would have been a revolution in diamond catching technology. Sometimes it goes wrong, right? Sometimes you do your best to use the tools that you've got, and it doesn't work, but you learn something, right? And that sort of experiment, that sort of lateral thinking, that's where the real fun with the tools comes along, because then you can work out ways to do something with them. And sometimes it works and sometimes it doesn't, and either way you learn, and he never tried it again. Now, it's not limited. You don't need a lab and all this sort of fancy equipment to let critical thinking drive what you're doing, to learn something from critical thinking. Now, this guy here, Donald Unger, he won the Ig Nobel Prize, one of the Ig Nobel Prizes, in 2009. And some of you may know the Ig Nobel Prizes are prizes for science that makes you laugh and then makes you think. If you don't know what they are, look them up, they're awesome. Anyway, so when he was 6 or 7 years old, his grandmother caught him cracking his knuckles. Oh, don't. I do this with high school kids, and there's 2,000 children start cracking their knuckles. Horrible noise. Anyway, so you know that thing, people, you sort of pull on your knuckles and it makes a sort of little popcorn noise. And his grandmother caught him doing that and said, don't do that, because if you do that, when you get old, you will get arthritis. But he wasn't taking her word for it. So for the next 60 years, this awkward sod clicked the knuckles on his right hand, but not on his left. And at the end of 60 years, he didn't have arthritis in either hand. And they wrote a scientific paper on it. And so it's not necessarily the recommended way of doing science. But you have to give him credit for not taking someone's word for it, working out that he could test it, and then having the dedication to follow through. So if he'd been wrong, he'd have had arthritis, right? But he learns something, and so there's a lot of little things in life, not necessarily as serious or as important as that, but you can try, you can have a go for yourself, right? Little problems, you can use some basic knowledge of the world, and you can test it out, and you can test your hypothesis, whether it's right or wrong. I can't see the clock back there. How much longer have I? Can anyone tell me what time it is? Because I can't see. Say again? 8:10. Awesome. Right. I've not run on for too long. That means what that means. Good. Okay. Now the reason this is here, so all this stuff about everyday physics is great, but let's go back to that problem of complexity. So the first thing is understanding the framework, the basic rules of the world. The reason this picture is here is that my grandfather, my mother's father, was one of the early television engineers. He trained as a mechanical engineer during the Second World War, and after the war he went to work for EMI, dealing with the early televisions. And back when he started, electricity was still really an immature science, an immature technology, and things went bang and pop and fizz and exploded and made smells, and you definitely knew there was something there, even if you couldn't see it. There was a very visceral connection to electricity. My mum, before I was born, was a computer programmer for Ferranti near Manchester, and when she started, she was programming in zeros and ones, just about. She hates me telling people that because she thinks it makes her sound old. I think it makes her sound really cool, so I keep telling people. But she was programming right in when computer code was, you could still see what the computer code was doing, right? There were these loads of paper tape with code written on it. And then my lab looked something like that. Loads of laptops, couldn't really tell you what they're up to. Might have studied the basic principles at some point. And the problem is that when you're dealing with this kind of thing, especially with things like touchscreens, it's very easy to get taken away from the basics of the physical world. And yet we still live in it, right? We've still got bodies that are about this size. We still have chairs that are about the same size. Toast still falls butter side down. And this is about the right size for a piece of toast. And the table is going to be about this high, so it's going to continue to fall butter side down, however many smartphones you have in the house. But the problem is that this sort of technology, it lets you be a little bit lazy, for a start, because there's a lot of things you don't have to worry about anymore, and you can't fix it anyway. Arthur C. Clarke, the science fiction writer, once said that any sufficiently advanced technology is indistinguishable from magic. And an iPad really is. Oh, there's Microsoft around here, isn't it? So what's it called? The Surface has passed that boundary by a long way. So, but in contrast to that, the internet makes possible more access to information than ever before. The problem now is not that the information isn't accessible, it's that you don't understand it when you get there because it's complicated. But that makes it really important, and it's the way to deal with all this complication, I think. The way to start is to understand the framework, because however complicated something is, it still has to obey conservation of energy. It still has to obey conservation of momentum. It still has to obey these basic rules. Someone might have done something very clever to make it happen very efficiently and make something quite clever happen, but the fundamental rules of physics are not broken, however magic the device seems. So I think this is really important because, there's lots of confusing things in the world, and brains just too much information, right? But the framework, when it comes to the physical world, the framework doesn't change. It doesn't apply to economics, because economics doesn't have a fundamental set of physical laws, but we have a fundamental set of physical laws in physics that are at the root of everything, and you can see them in the simple things, and the same things apply to the big important things like energy supplies and medical testing devices and all that kind of thing. So I think it's really important that we don't trivialize these toys, because that's our way in a complicated, confusing world. Noticing these little things about the world that teaches the basic physical laws that provide the framework for everything that happens around us. That's an important thing, and everyone can try it. The time I knew when I might have done something useful with the book, so I gave it to. I'm a badminton player. Probably most of you never heard of that sport. I don't know. I like it. But my club in Wimbledon in London is, there's lots of people there. They know me as an athlete. They don't, know much about my science. So they're very good for constructive feedback. And I sent one of the draft chapters to one of my friends at badminton, and I got a text message back from him a few weeks later, and it said, so he was working overseas in Switzerland, and the text message said, "I'm sitting at breakfast in a posh hotel in Switzerland, and I really want to push toast off the table because I don't believe what you wrote." And that's the good bit. He doesn't have to believe me. He can just annoy the waitress, right? But he's free to push toast off the table and watch it happen for himself. And if he doesn't agree with me, he can push toast off the table in front of me, and we'll both look at the evidence. And look, they're not inaccessible, right? It's right there, and you can play with it. And it just takes a bit of habit and a bit of confidence, because physicists are not very good at about sharing. I think the idea that this isn't just about knowing things; it's about your perception of the world, that your perception of things changes, and you walk around carrying that, and it's very useful, and no one tells you that. So I've told you now, so you all know. So we'll skip that bit. Right. So the other thing that isn't going away is the complexity. Having dealt with the fact that maybe we can do something about those foundations, the other thing we have to deal with once we understand the framework is being comfortable with ambiguity and being comfortable with the difference between not knowing everything and knowing nothing. The reason this picture is here, so Horizon is a very long-running series of BBC Science shows, and we made one in 2004. That's me and one of Britain's weather forecasters, John Hammond, and we made this Horizon. So we had a few unusual winters of weather in 2013-14. And we made this show about why that had happened. And if the BBC had ever understood how complicated the answer to the question was, they wouldn't have let us make the show, so we didn't tell them. Because there's all these things, weather's complicated, right? You get this a lot here, because your weather map includes a much larger area than ours. But you've got El Nino doing things, you've got the jet stream doing things, you've got something called the quasi-biennial oscillation going on over the equator, you've got the North Atlantic oscillation, all these different things going on, all these patterns overlaid on each other. And so we understand a lot about the weather. We don't understand everything. The weather scientists can piece together why these winters were particularly bad, but it's not as simple as A causes B causes C. It's, this happened and that overlaid with that, and it corresponded with that. Hard to predict in advance, but afterwards you can kind of trace back. And the important thing is that there's a huge difference between not knowing anything and having that sort of knowledge. Can't say it in 2 sentences, but there's a huge amount of understanding. And I think there's a sort of there's a point coming up where this is what science is like now. All the interesting bits are in that complicated bit in the middle. And the problem with the complicated bit is that the foundations are still the same. You can explain the basics of weather with the gas laws and thermodynamics and various other simple patterns. When it comes to the intricacies of how they play out, you use the same rules to explain it, but it takes, a long essay and not 2 sentences, and you have to put a little bit more work into putting all the pieces together. So in order to trust a weather forecast, fundamentally you have to trust the system that the weather forecast is based on. And the system is science. The system is, we've got some evidence, we're going to test the hypothesis against it, we're going to revise our opinions and get some more evidence, and sort of work our way through it. So because things are complicated, you have to trust where it comes from in order to trust the overall thing. So being comfortable with uncertainty and understanding that, what it means to have understanding of a complex system, I think that's a very important thing, because there is never going to be an answer that is just one thing. So on a slightly more cheerful note, I think each of us has 3 life support systems: a body, our own body, our planet, and our civilization. And each of them is keeping us alive in its own way, and they're independent systems. And for example, one of the reasons that climate change is an issue is that it's 2 of these life support systems butting up against each other. We've got our planetary system, which ticks along, and we rely on it being as it is, because it keeps us alive as it is now. And then we've got our infrastructure as a civilization, which keeps us alive in terms of supplying food and water and growing enough stuff and all that kind of thing. And we have to negotiate that boundary. But each of these lives, I mean, so there's all these reasons for studying science, which are, it's interesting, it's funny, you can play with eggs, and it satisfies curiosity, and all this kind of stuff. But if you're more pragmatic than that, this is the reason for doing it, is that if you're not interested in anything else, you're probably still interested in keeping yourself alive. And the rules that keep these life support systems going are the basic rules of the physical world. They're the patterns of physics that you can see in your kitchen. So it's probably quite important to understand them. And these all end up being quite complicated systems, but the fundamental layers of understanding are built from the same things. And so that's my, if you're not convinced by physics just being interesting, hopefully you're convinced by that as a reason to study things. So, this is a kind of class-like environment. It's got to be homework. So things for you to try at home to get you started on playing with toys. So lemonade in Britain, I need to change that for US audiences. We are very unsophisticated with lemonade. What that should say is soda. Because in Britain we call stuff lemonade that has never been near a lemon. But you are better than that, sometimes. So Sprite doesn't count. So anyway, bottle of, whatever 2 litres is here, bottle of fizzy stuff. Take the label off so you can see. Stick some raisins in the top, watch what happens, it's very interesting. Also very good at parties if you're with boring people. Pick the raisins out of the bar snacks and find yourself a fizzy drink. It's got 2 effects. It makes the boring people go away and it makes the interesting people come to you, so you win both ways. Spill some coffee and leave it alone. Take a picture of the spill, and then come back a bit later and take a picture of what's happened to it afterwards when it's dried. There's a really important difference that you've all seen that is worth looking at. Get a teaspoon, if you can't be bothered with the mess, get a teaspoon and get a ceramic coffee mug and tap it around the rim and listen. That's a good thing to do. And push some toast off a table, because you might as well. There are ways, and see if you want to extend that one, see if you can find a way to knock it off in a way that it doesn't always fall butter side down. It's messy, right? There is a physical solution. It is quite messy, but it's worth trying. So I'm going to stop talking, and we have time for questions, but that's me done, thank you.
So if you do have a question, we ask that you come and ask it at the microphone and keep your question in the form of a question. Thank you.
And feel free to ask about anything. I mean, anything within reason. You've got a race going on here. Who's going to get there first? Go on. Oh, God, he's got notes.
How do you develop the practice of finding patterns?
Say that again. The process of finding patterns.
How do you practice it? How do you find
Practice?
it more? Yeah.
Well, my publisher would say read the book. But you start by looking. It starts with looking for things that are the questions a kid would ask, and then looking up why. That's in the modern world. That's the easiest way to do it. And it's a habit. It's really hard to unsee the things or to re-see the things you've stopped yourself seeing. So, but once you spot one, hold on to it, right? You'll have those little thoughts that drift through your mind that say, "Oh, isn't that odd?" And it starts with, at that point, not dismissing it, right? File it away. You'll see something, right? And even if it's, contrails in the sky or the way that ripples travel across a pond, there'll be some little thing and you go, "Oh, that's a bit odd." Hold on to that and then look up why it happens. That's the first bit. Better than looking it up, if you could try and think of reasons for yourself and play with it a bit. But it starts with catching the thought. Adults are always suppressing things, right? That's what part of the process of growing up and being an adult is, that there's too much complication in the world. So your brain just you learn to suppress anger and you learn to suppress frustration, and you sort of, you're always putting the lid on yourself. When it comes to science, take the lid off and just hold on to what came out. So that's the place to start. Yeah, and those around after that. Yes, I'm over there.
I'm not sure the British practice of making tea, but I was wondering if there's a tea bag involved on your walk back to your office, and if that would be analog to that pendulum in the building.
So so the way the tea bag has got two effects it could have, actually. The first thing is that if you make tea properly, you take the tea bag out before you put the milk in. I wish someone would teach Starbucks that. Anyway. So if in an industrial setting there's this sloshing process, one of the common ways of preventing it is to put baffles in the container, which is to put in things that stick out and are obstacles to the sloshing movement, so inside, underwater. So a tea bag would definitely do that.
So a teacup with bridges would be?
Yeah, so if you can face the washing up, the way, what you want sort of little shelves coming out on the inside, that's what an industrial engineer would do, who didn't have to do the washing up. The other thing you can do is have a mug that kind of comes around a little bit to hold the sloshing in. And then what else would a tea bag do? Let's have a think. You would get a bit of swaying. But the swaying, there's an interesting thing there with inertia. Let me think about that for a bit. Because the tea bag isn't free to sway in the same way that the pendulum is. And so its range of motion would be very limited. Maybe it might depend on whether you had a pyramid tea bag or a flat one and which way it was oriented. You should do the experiments. I think the major effect would be it acting as a baffle and just getting in the way of the fluid trying to move past it. Because in order for that sloshing to happen, the fluid underneath has to move as well. It's not just the bit on the top, but the fluid all the way down is actually shifting a little bit. So if you stop that process. So that would be my guess. But then so we can all do the experiment now. Go home, next time you have some tea. And the other thing the tea bag could do just a little bit is reduce the depth of the mug effectively if it was sitting on the bottom. So lots of experiments to do. I don't know the answer, but you can all go and try. That's the best I can do with that. Yes?
Hi there. So that's quite an interesting job application of physics. Your friend in this case blasting diamond parts and then trying to analyze that. I'm sure it happens both ways, but when you're a physicist and you're looking for a job, I mean, do you typically find more often those, you got the one crazy idea and you're just going to make a job of it and get someone to pay you for it? Or do you find it more often after you've decided that you like this bit of physics that now I'm just going to search for jobs in this arena?
People don't always pay us to play with toys. That is a sad thing. So, yeah, exactly, boo. What normally happens is that it's driven by an application. So it depends on, there's pure physics research and applied physics research, and ideally you're always doing a little bit of both. The pure stuff is when you see an interesting thing and you go after it. The applied one is when there's a problem and you find ways to solve it. When you're an academic physicist, you can do all the experiments you like as long as you can find a way to pay for them. So there's always a bit of a balance. It's not like you go after. I mean, there's so many answers to that question, but normally you create an opportunity that lets you do something interesting and assume it's going to take you to the next interesting thing. So it's not like you go after a single goal. You go, oh, here's an interesting thing, and that takes you to another interesting thing. And so you turn jobs into what you want them to be because you're interested in what you're good at. What interests you will be something you work at, and therefore you're good at it, and then it takes you along that. So it's not like you get to pick. There's no simple answer to that.
No,
I don't think.
that's fine. I was just curious your input. Thank you.
Just for the record, all questioners so far have been very homogenous in terms of their gender. If any other people, no, they haven't. That's not quite true. They've been quite homogenous, but not complete. But let's have a mix of people coming to the microphones. Right, go on. You're still allowed.
I'm okay then?
Yeah.
Okay, I gotta, you have to at least get me started with the toast thing. So I think what's going on is that the butter has a greater mass than the toast.
It's nothing to do with the butter.
Oh, really? Okay.
You can
so
try it without
I'm-
butter
I'm
on it.
completely, okay, so I haven't got a clue.
But you see, you could have. But you see, you could have. All it would have taken, right, is for you not just to do the thinking, but actually to go and get 2 pieces of toast and put butter on one and not on the other and watch, right? It's not about. I'm constantly trying to teach my students not to. Especially the young ones, not to think they can think through a problem and just get to an answer. You've got to check along the way against reality. So before you go off about thinking up some enormous hypothesis about whether it's about the butter, what you do is you try it with butter and without, and you see if there's a difference. And if there isn't, then you get off the topic of the butter, basically. There's this sort of like, humans are always trying to think. Part of the discipline of science is not thinking too many steps ahead. You've got to prioritize the first problem and check, and then you find out whether the next problem is worth worrying about. So yes, sorry to shoot you down, but it's not about the butter. Yeah.
Your agenda question actually piqued on something that I was thinking about, that picture, wonderful picture of all the men in physics, and then you. How do you get more women involved in physics? Because it really is, it could be very exciting.
That is a question that's got an hour and a half answer, which I will spare you. But the first thing everyone can do, if you're interested in this, is read a book called Delusions of Gender by Cordelia Fine. And it's about the socialization of brains and how fundamentally, above everything else, humans are social creatures, and we are programmed almost to behave in the way that we think people expect us to behave. And so having a gendered society creates problems that are very hard to escape, because your brain is constantly, even though you're not aware of it, saying, what am I expected to do? So the first thing is, everybody needs to read that book, which is referenced to the hilt with very solid academic references. The biggest thing is changing the environment. So science has traditionally been seen as something which is, it's about right and wrong. It's almost an aggressive our way or the highway type thing. And it's not traditionally seen as being about conversations. And the manner in which a lot of physics departments and engineering departments still operate is very old school aggressive male. And changing that culture is the biggest single thing that will change the number of women in physics. And that involves the men accepting that modernizing the workplace is better for everybody. It's not doing things for the women. It's modernizing something which makes it better for everybody there. I'm very proud to work in a department at UCL where the people who go home at 4 o'clock to collect their kids and then make up the hours later are the men, not the women. So I think really there's lots of types of diversity that, we do not have a diverse scientific workforce, and that is a huge problem. But making it better is about making the system better for all humans. We need to work harder and in very specific ways for some sectors of society. But the idea has to be pushed forward by everyone because it's better, not because it's giving something to somebody else or sort of creating friction. It's better for everyone. So it's an attitude thing. And there's all these things about the leaky pipeline and, stereotypes and why women stop doing it. And there was a report that was published in Britain 3 or 4 years ago that suggested evidence at the moment. The reason women leave physics is because they've got better things to do. They can do the technical stuff and the social skills. So they go off and get paid huge amounts of money to work in industry. So there's lots of different ways of looking at it, but that attitude change, that it's a modernization process and it's not optional, and culture change has to be taken very seriously. That's a hard, because people assume, everyone thinks their thing is normal, right? And that there's a lot more listening needed about different ways of the way you can run science. So yeah, it's a hard problem. Over there, somebody.
These will be our last 2 questions.
Last 2 questions then.
So I know that that the quantum mechanics, the things that are very small follow one set of laws, and the things that are very large follow another set of laws. Can you talk about sort of the stuff in between and what laws they follow?
So yeah. So the interesting thing about scaling laws in physics is that all of the forces are present all of the time. But there's always a sort of hierarchy of priority. So for example, where I am, standing on stage, gravity is the force which is making most difference to my body immediately. You know, there are electrostatic forces, there's the strong force and the weak force, there's surface tension and viscosity of the air and all kinds of things, but gravity dominates because of this size. So all of the forces are always there. So shear forces from viscosity, for example, I can move my hand around, but the viscosity of the air is basically negligible. So that doesn't make any difference. But if you were to make my hand really, really small, the viscosity of the air suddenly starts to matter more than the gravity that I need to resist to hold my hand up. So as you make things smaller and faster, exactly the same laws are there, but different ones are at the top of the hierarchy. And so that's why a towel, for example, if you get some absorbent tissue and you put it in a puddle, the liquid will only soak up so far, and the structure of the towel is what dictates how far that is. But if you got something that was quite big, like a kind of play frame with great big holes this big, you put it in a puddle, nothing would go anywhere. So it's all about the hierarchy, basically, and the same simple forces apply. And the ones that don't matter are so insignificant most of the time that we can completely discount them to a good approximation. So it's an interesting problem because you shift, and it becomes very interesting when you do things like working out what life will be like on another planet, because there you have the same physical laws, but you've got different, they've got different values. So the hierarchy could be different even for something my size. So it leads to all this interesting sort of speculation about how you operate in different environments. And the first example is the ocean, because if you want alien life, don't bother going to Mars, just go to the bottom of the ocean. Far more interesting. Right, I'm sure we're running out of time a little bit here. Yes, go on, last question.
So one comment to the gender thing is giving women the opportunity to rise to the challenge. So challenging women to come up and ask questions is the first thing that actually gets us up here to do it. So just one comment on that. My question was very similar to hers, so I'm going to switch it up a little bit. Do you think that we have all the tools necessary to create a universal theory of everything, and is that possible?
Philosophy. Let's finish on philosophy. So, universal theory of everything there are different interpretations of what that means. At its broadest sense, it's a set of consistent theories that explain everything we see experimentally. Theory of everything, the grand unified theory, is this thing where quantum mechanics and general relativity have to mesh, but they don't play nicely with each other. Black holes are, one thing. Tiny quantum stuff is another thing, and they might be quite far apart. Those two theories don't have to talk to each other until you get inside a black hole or back at the beginning of the universe. So there's a set of grand unified theories. We know that quantum mechanics and general relativity cannot both be perfectly right, because they have to talk to each other at some point, and at the moment they can't do it. So there's that kind of grand unified theory where there's some modification needs to be found, but no one's quite found where the matching process is. When it comes to the bigger question of whether a theory of everything is possible, I think that history is littered with scientists who thought that it was just about the tidying up now. We've basically found anything that's just about tidying up. So science is full of surprises. I think that the reason I'm hesitating is that for it to be science, it has to be testable. For you to have a theory, it has to be testable. And a lot of theories about the universe and multiverses and things like that, it's very difficult to test them. So it may be possible to have theories that explain everything we see, but there could be two of them that both explain everything we see, and we cannot distinguish between them because we can't create an experiment, because we can't go outside our own universe, for example. So it is likely that something will not be testable, but it doesn't mean that we can't get very, very close. And the fun, I can't think of anything worse than science. As a friend of mine once said very, very well, science knows it doesn't know everything because otherwise it would stop. And it would be, it's such fun to do, and it's such a fun journey to go on, but it would be a terrible thing if it was to stop, because it wouldn't be fun. So maybe I hope we don't ever find a theory of everything, because then we'll keep having fun, and maybe that's a good place to finish. Thank you.